Okay, now the last item of our discussion is pushover analysis using CSM. And as I told you, the seismic performance-based design that we are talking about is centered around this pushover analysis. Okay. So I want to give you a complete background of pushover analysis, and it's easy to understand. There is nothing difficulty in it, but its implications are great. That's the most important thing. Okay. Pushover analysis means that you can see that there is a tower and it is tied to a rope and there is a vehicle which is moving. As a result of this tower is given a displacement. Okay, top is giving a displacement. Now, when it is giving a force over there, you can see at the base there is a opposite force B acting. So you can plot base shear versus roof displacement. As the roof will displace more, you will require more force. And whenever there is a more force, there will be more reaction over here. So this plot could be of this type if it were perfectly linear. That means force and displacement relation is perfectly linear, then the curve would have gone straight. Right? But it is not linear, it is non-linear, and as a result of that you can see partly it is elastic, then after that it goes into the non-linear means inelastic range. Now this is a simplest example of plotting a base shear versus roof displacement curve. Now when we come to the actual applications, we take buildings. And these buildings can be given a force or push in different ways. The most common push is shown on the right hand side. On the top of the building, you are giving a delta push, right? And you can plot, as a result of that, there will be base shear. As delta RT increases, base shear increases, and you can see that some portion in the beginning, this is linear, some portion in the beginning is linear, then it becomes non-linear. It means that up to this, there is no plastic hinge that has formed. None of the portion of the structure went into the inelastic state. They are all elastic. Okay. That's why it was linear. But after this point, gradually inelastic deformation started taking place in the members. Inelastic deformation means some of the points the yielding took place, hinges formed, and one by one hinges formed and leading to a flattening type of thing, and maybe after some time it goes down, it fails. Okay. So this is what is the pushover analysis. We push over here And we will see later in the slide there are two types of pushing or pushover analysis. One is force based pushover analysis, other is displacement. Right? And what you were learning yesterday, last 2 days, were displacement based design. Okay, that means the pushing basically is based on the displacement, not force. Now this is another kind of situation. Say the displacement over here when you are giving, you are not sure how the other stories are displacing. You do not know. You only know that you have displaced this portion. You don't have any idea about how they are moving. But it may be possible to push it or displace it in such a way that displacement of the floors are having some relationship among it, some predetermined relationship. I can push it that way as well. How we do that I will explain. And this is of course an asymmetric building, so which is stationary. Now in the next slide, you can see an important thing which you know already. I have a VB by delta T plot. Now this VB delta T plot can be converted into SA SD plot. What is SA and SD plot? That I'll explain little later. But important thing is that we convert this into this format by some means, and that is how it is done. Okay, with the help of this formula. How we come to this again, that I'll explain later. But important thing to note is that in the pushover analysis, using CSM technique. Now the way CSM is coming. CSM technique, what we do is that VV versus delta RT, this plot is converted into a SA-SD plot. SA and SD plot means SA is the spectral acceleration that all of you have done in your earthquake code, where there is a SA graph is given. That is SA. Okay. And SD is nothing but the SA divided by omega square. Alright? So say this is your SA by T. For different time period, you have SA known. This is the curve which is given in the code, spectral acceleration curve. And if you want to design a structure for design force, you want to find out for a corresponding time period or frequency, you find out the value of SA. All right. Now this time period is the time period of the structure or single degree of freedom system. And 2 pi by T is your omega n on natural frequency, that all of you know. 2 pi by T is omega n is natural frequency structure. And SD is nothing but SA divided by okay. So this VB delta T plot is converted into SASD plot. This is the crucial thing in CSM. Okay, the name CSM has come from that, and we do this converting into SASD. Right? Yes. Now comes the understanding of pushover analysis, concepts of POA. You take any particular building, okay? And in this particular building, what you are doing is that you are providing certain forces, not displacement. Okay? This set of forces are P. So you can write down a matrix equation. This matrix equation is K matrix corresponding to the degree of displacement. So what will be the size of your K matrix? What is the size of K matrix for this? Yeah. So P, what is the degree of freedom of P? What is the size of vector P? Size of vector P. Four. So 4 by 1 and K by K will be also 4 by 4. But actually K is not 4 by 4 because there are rotations. Okay. These rotations are condensed out. After condensing out these degrees of freedom, you can make it a K. And if you remember, condensation procedure means nothing but elimination of the variables. So if you have got in 6 by 6 degree of 6 by 6 equation, then you can reduce it to 3 by 3 equation by eliminating 3 variables. Isn't it? Yes or no? Yes. This game you have done in your algebra, basic algebra. So that is condensation. So here in the writing down the stiffness matrix, you have the sways, force sways, and rotations. Rotations you condense out, they are the set of variables condense out and keep only the 4 displacements. So that's how K becomes 4 by 4. समझा कि नहीं समझा? ये बोला है मैंने पहले. इसमें कुछ ही this condensation is nothing but elimination procedure. ठीक है? Okay. Now this K matrix is assembled from elemental matrices. That means each beam and column has 4 by 4 matrix, right? 1 rotation, 1 translation, 1 rotation, 1 translation, 4 by 4 matrix. These matrices have been assembled first. Then you have rotations, displacements, then rotational degrees of freedom are condensed out. Finally, you have got 4 by 4 matrix. So this is your usual matrix analysis. Now, if you solve this, you will find out D, and once you find out the displacement D, you can find out dj. Okay. dj means the displacement at the ends of the members, and once you know the displacement at the ends of the member, rotations and displacements, you can find out the fj. What is the stasis in the member? You know displacement, you know rotation, you can find out moment. इसका बीमारी क्या है नहीं? Okay. Fine. So इसमें there is no problem. Now we come to another thing. The types of loading. We are talking of force still. We are not talking about the displacement. The force that we can apply. onto this particular structure. Could be a single force at the top, or there could be this is the top load only top load. That means this and this point, zero load. Right? This is one type of loading. This is arbitrary loading. Right? Any load, they don't have any relationship with other. Then you can have a uniform loading. Same load all through. Then you can have a triangular loading. Okay? Triangular variation. Then you can have parabolic variation. So different kinds of variations of loading are possible, okay, including a single load. And the last one is called a modal load. Now what it means, that this building, when pushed, it takes a shape. Which shape it will take, I do not know, because it depends upon the stiffness distribution. Right? So note this word, stiffness distribution. Say there is a bamboo. This bamboo is having a greater diameter towards the bottom, and at the top the diameter reduces. Now if you push it, okay, which portions will comparatively move in the pushing direction? Which portions will have a higher? The higher displacements will be toward the top. And as you go down, the displacements will be lesser, comparatively less. What does it mean? It means that it displaces according to the stiffness distribution. Alright? So, primarily, the displacement that it takes place when you push it, the distribution of displacement is guided by the stiffness distribution of the system. Okay? Now, what we are talking about over here, that means if I go back to the previous slide, not sorry, previous slide. Yeah, this slide. For example, when it is top load only there, then I am pushing, so not pushing, I am giving a load over there. Then the displacement of these points will be guided by the stiffnesses. Okay? It will be guided by the stiffnesses. So, one thing that dictates the distribution of the displacement is the stiffness distribution along the height. Okay? Is it clear? Okay. Now we are coming to a different terminology called modal displacement. Now, modal displacement means, and modal force distribution means, that this particular building frame is allowed to vibrate freely. If it allowed to vibrate freely, there will be a natural frequency. If it is a single degree freedom system, it will have one frequency. We'll see later in our dynamics course that it is a 3 degree freedom system. It has got 3 frequencies, not one. Okay. Out of that, one frequency will be having the least frequency, or called fundamental frequency. Okay. And if I pull a structure and let it go, then it vibrates in its fundamental frequency, on the natural frequency, which is the least of the three. If it is 3-degree freedom system, then out of the three frequencies that it can have, the least frequency will be that if I pull it and let it go, it will vibrate in the fundamental frequency. Can you tell me why? Fundamental frequency means least frequency. Okay. And what I am stating that I have pulled the structure and let it go. And it is vibrating of its own. And vibrating in the first frequency or the least frequency. Can you tell me some, from your common sense, some reason for that? बताओ. कॉमन सेंस लगाओ, इसमें कोई पढ़ाई लिखाई का नहीं है. दिस इज वेरी कॉमन सेंस. टाइम पीरियड में क्यों जा रहा हूं मैं? कॉमन सेंस ने बोला तुमको मैं पकड़ के पढ़ने को धकेल दिया, पढ़ने का लिए धकेल दिया, ठीक है ना, और डर के चला गया, उधर खड़ा नहीं रहा. तो मैं चला जाने का बाद तुम जब पढ़ते रहोगे, बहुत जल्दी जल्दी पढ़ोगे कि धीरे धीरे पढ़ोगे? पढ़ेंगे नहीं तो ठीक है, बस पढ़ेंगे नहीं का बराबर होगा, बहुत धीरे धीरे पढ़ोगे. So, the thing is that if a person, if anything in the world is asked to do anything of its own, it uses the minimum energy. Okay. So in the minimum energy, basically, you will perform the work. Okay. And minimum energy means slowly oscillating. Clear? So it vibrates in the least frequency, or that's why the fundamental frequency all the time, the least frequency out of all the frequency in which it can vibrate. Is clear? So now we are coming to that whenever we have a least frequency in its vibrating of its own, then there is a particular shape in which it vibrates. That means it may not vibrate like a triangle, but it will like this, and it will be vibrating this way. There is a particular shape. The shape also will be such that the energy in the system required will be again least. Okay? So there is a shape in which this will vibrate, and this shape will be such that it has the least strain energy. Is that clear? It cannot have a high strain energy because that is a natural thing. It's clear to all of you? So now let's say for this building there is a fundamental frequency, and correspondingly there is a shape which is called fundamental mode shape, and in this fundamental mode shape it is vibrating. Okay. So next thing is that what we are saying, the load distribution is such that it follows the mode shape. That means if here it is P1 and then here it is P4, P1 to P4 will be a relationship, and that relationship will follow the first mode shape, a curve. particular car. Clear? So now say we are able to apply the load in such a way that the first mode shape, that means loads vary according to the first mode shape of the structure. It's clear? So the load now has a specific ratio between them, and that ratio follows the first mode shape, and that's why we are calling as the modal load. First modal load. Clear? So what I am saying, want to say is that there are various types of loading possible. So these are all understandable. This one, this one, this one, this one, this one are all understandable easily. This one has got some difficulty, but that I have cleared down. I can have a load distribution, which I am calling the modal load distribution, and I can apply that load also. And as a result of that, the structure will deflect. Okay? So this is the different type of loading possible. So this is what is the force-based pushover analysis. Okay, force-based pushover analysis means I can apply different types of forces, and these forces I apply incrementally. That means in steps. Delta P1, delta P2, delta P3, delta P4. That way I can go on adding and increase the load. So this is what we call the force-based pushover analysis. Okay. And you can solve this problem very easily. K matrix is known, P vector is known, the load is known. You can solve the problem and can find out bending moment, shear force, etc. Okay. Now the summary of the force-based POA is that force is incremented proportionately, right? Incremental displacements are obtained. For each increment of load, you can have incremental displacement added to the previous displacement. Next force increment is added until the desired displacement of the top is achieved. That means you have said, you decide that this much of displacement I will allow. So you can go on pushing the structure till then. And forces in the members for each step, you can calculate, add to the previous one, and get at any state what is the force. Okay. That's the force-based pushover analysis, which is easy to understand and which you provide in, you can, at the top you are providing a force. So all right, okay? Clear? So before I go into the displacement-based pushover analysis, I have talked about the force-based pushover analysis, where you are applying the forces. Now we are coming to the displacement-based pushover analysis. Okay, which topic of discussion. In displacement-based POA, displacements are incremental. Okay, in place of giving a force, you are giving a displacement. Okay, right? Now this is an anomalous thing. How can you create displacement? How can you give displacement without applying force? So all displacement based design persons they basically are new generation people. Okay, old generation people, they never recognized displacement based design and all that. They were very classical people. They thought about only force. Okay, force is acting onto the structure, and there is displacement. Force acting, you can see visually. Your force is acting. Whenever there is a displacement based problem, the question is how there could be a force or a displacement without force. How can you practically give it? Now say, मैं रस्सी से पकड़ा कोई बिल्डिंग को टॉप को जो खींच रहा हूँ धीरे से टू सम डिस्प्लेसमेंट ओके लेकिन वो डिस्प्लेस हो कैसे रहा है फोर्स का लिए तो हो रहा है ना सो एक्चुअली इट इज ए फोर्स वेयर अप्लाई बट इसको जार्गन को उल्टा दिया ये लोग राइट and it created a new kind of design philosophy called displacement based design philosophy. Okay, there is a reason behind it. Reason is that they want to keep a control on the displacement, not on the force. They say that I will allow the structure to displace to certain extent, and accordingly I will apply the force. Okay. And based on that, all our calculation or design etc. will be centered around that. So that is the displacement based. Or in other words, in single word if I say, then the force based, you have a control on force. In the displacement based, you have a control on the displacement. Okay. Whatever is the force, that will automatically will come because of the displacement and providing. In the force based, I am not bothered about what is the displacement. I am bothered about the amount of force I am giving. So these are basic difference. So अभी तुम लोग सब ने because ये is a thing which does not come into the understanding of most of the people. So all of you will say with me, force based, बोलो force based.
Force based.
Problem means there is a control on the force. Displacement based. There's design or analysis means there's a control on the that's all. Nothing beyond that, okay? So I'm controlling the displacement. All right? Yes. And from that point of view, we'll go ahead. And we can see that striking differences are coming between the two. Let's see. However, unlike force-based approach, any type of displacement distribution and corresponding unidirectional load distribution pattern cannot be achieved. Okay. Now, in the force-based, we have seen that we can implement any kind of force distribution. It's all right. From single force, uniform force, modal force, triangular force, any kind of force I can provide. But here, however, unlike force-based approach, any type of displacement distribution, that means if I say that any type of displacement distribution I will provide, I cannot do that. And corresponding unidirectional load distribution pattern cannot be achieved. Now, let's say the let's say the displacement at the top only. Okay, if I put displacement of the top only, the corresponding load distribution pattern should have been at the top only. I am giving displacement corresponding should be at the top, but it is not so. The moment you give a displacement on top, you will have a displacement all through. So displacement at top only there are, so this particular cannot be achieved. I have crossed. Now, let's say I want to have uniform displacement. Okay, all places will have uniform displacement. Can I have a load like that? Unidirectional, in the same direction? No. You have to put a load on this, or opposite side loads, so that finally the displacement becomes the uniform. So unidirectional force I cannot develop distribution. Is that clear? Yes or no?
Yes.
So I cannot have it. Then arbitrary displacement. ये तो हो ही नहीं सकता है, right? You cannot give a arbitrary displacement and you can have a distribution, force distribution. You cannot do that. This is only which is possible. That is a smooth variation from 0 to maximum. That you can do. Because the nature of displacement will be like this. If you give a displacement, the structure as a whole will displace. And when it will be displacing, it will have a smooth curve. Has to be a smooth curve. Is all right. Whatever be the loading, it will, if it is unidirectional, then there will be a smooth displacement. Is it clear or not?
Yes.
I am talking of unidirectional. So if you give a high load, small load, again a high load, whatever load you give, but if it is unidirectional, the displacement pattern will be a smooth pattern. Right? May have a cubic shape, may have a parabolic shape, can have a what we call mixed shape, whatever it may be, but it has to be uniform. Clear? So a smooth variation from 0 to max, this is possible if it is unidirectional, and I can compute the moment this displacement is given to me, I can calculate the force. That force will be K multiplied by D. Force. ठीक है? Okay. So, what is the implication of this? Implication of this is that in a displacement-based concept and unidirectional pushing, if these two things if you are bringing in, then the displacement pattern over the structure should be a smooth curve. Right? Whatever be the, and accordingly you can find out the load. Clear? So that is the first difference. As opposed to that, you can see that in the types of loading, all types of loading are possible, and consequently the displacement. But in the displacement based, all types of unidirectional loading cannot be constructed. That's the most important thing. समझा कि नहीं समझा? An incremental displacement applied at top is the most common pushover analysis which can be realized in practice. That means I am pushing the structure at the top only. That's the most common. Because of the prescribed displacement at the top, displacement at other points do take place which are not known. You do not know. I am pushing at the top. What will be the displacement at other levels? I do not know. Can this displacement be known? Note that the displacement at other points depend on the stiffness properties along the height of the frame. That's what I've told you. They are not constrained by way of any load pattern and take place freely according to the stiffness distribution. Okay, if I push it, it will have a shape according to the stiffness distribution. It is not constrained by any load pattern. Now I want to solve such a problem. That means I have on the top, I have only one load. Okay, I am giving a load, and obviously I know there will be displacement at other points. And that displacement has to be continuous. Any displacement has to be continuous, okay, which are not known. And I am trying, can I find it out? Yes, I can find it out. Let's see how we can find out. Okay, that is the most important thing. How we can find out? I am giving a displacement only at the top. So, I start with this problem, K into delta is equal to P vector. P is on the top only there is a force. In other places there is no force. All 0, 0, 0. Okay. So I find out delta is equal to K inverse P. So you can find out the displacement at all points. निकलेगा? Yes or no? ठीक है? अभी तुम लोग तो ए से कर लिया. अभी बताओ K11, K21, K31, K12, K22, K32, K13, sorry, K31, K32, K33. तीन वेक्टर है. I have a 3-story frame. I am putting a unit load over here. Right? Okay? Now tell me, what will be the displacement at 3 points? I have given a displacement, sorry, I have given a displacement over the top one. Okay. At the top, what will be the displacement at other points? This is the first question. Second question is that what will be the force at other points? I have given a displacement only. डिस्प्लेसमेंट दिया है, ऊपर में भी कोई फोर्स दिखाई नहीं दे रहा है. ऊपर में मैंने डिस्प्लेसमेंट ही दिया virtually. I have specified some displacement, say 1 centimeter. How I have applied, not known. It is 1 centimeter only. Is there a corresponding force in the system? And if that is so, what is this force? And say the displacement is unity. बताओ. Then K21, K31, K31. right? Because 1, 0, 0, if you multiply that, this is a force. So, if I am giving a displacement at the top, of whatever way I have given, the force basically is K11, K21, K31. And you can see immediately that this is according to the stiffness distribution of the frame. Okay, I've given it of displacement. Okay, and force is this, three forces coming into this system. Now we come to the next problem. Here what I have done is that you have defined the forces. These are the forces. Now what will be the displacements? Okay, corresponding displacements. So delta is equal to K inverse P, and because P is basically has a 0, 0, 0, K inverse will be 3 by 3 matrix. Now if you multiply with again 1, 0, 0, you will get the first column of the inverted matrix would be the displacements. Okay. So let delta at the top is delta T. Then delta J by delta T is the ratio of displacement of the Jth. All right. In the previous case, it was K11, K21, K31. Now inverted matrix first row will come as the displacement. If delta E is the incremental displacement applied at each increment, then the displacement of the jth flow will be delta Ej will be delta J by delta T divided by delta E. Delta E is at the top. Okay. So you can find out the displacement given at the top and corresponding to the displacement at the other points will be guided by this. That means top displacement that in delta E is given to you, or so delta E T is given to you, the maximum displacement for this case for force applied at the top, and from this you can find out the displacement at the other points. Is it clear? So what is the problem that you can see beneath it? Beneath this, there is a problem that in order to get the displacement best, you are giving a displacement at the top only, okay, and trying to find out the displacement at other points. Then you need to first solve the problem as a force-based problem, giving a unit force at the top. Find out the value of delta T. Once you find out the delta T, then you can obtain the value of the other displacements. All right, in the displacement base. Now this is so far as the top displacement you are giving, only displacement at the top. And other displacements are not known, but you can calculate. And for calculating, you have to divert back to first the force-based analysis, then you come to the displacement. You can find out the displacement. Now we straight away come to the modal pushover analysis. And as I told you, modal pushover means that the displacement pattern will have a particular shape, and that shape will correspond to the first mode, usually first mode, but you can make it coincide with any other mode. Okay, that's the difference. But let's, for the timing, say that we are only trying to make it a first mode shape. So first mode shape is, say, known to you, given to you. That is, you have pulled a structure, let it go, and it will move in a particular way, that is my first mode shape. And I can calculate that. Okay. This mode shape is given. So now what I am trying to say is that the modal pushover analysis, the displacement is incremented at the top, right? At the top I am giving. During each increment, a unique relationship between the floor displacement is maintained. That means I am putting a constraint now. Unlike the single force that I have given at the top, okay, and allow to move it freely of its, or move it in its own way. I am not doing that. What I am saying that I give a unit displacement at the top. All right. And I increment, or not unit displacement, small increment. And I am incrementing like that. But I am putting a constraint. Constraint is that although I am giving a unit displacement, I don't allow the other floors to displace as freely as possible. I am putting a constraint. Constraint that the other floors will displace in the first mode shape pattern. So that means if delta E is the top displacement, then other floor will bear a relationship with that. Okay. So that is called modal pushover analysis. Okay. It is different from ordinary pushover analysis where I am giving a top displacement. Only top displacement, only I am giving without having any relationship with the other floors' movements. The unique relationship is defined by the first mode shape of the structure or any other mode shape it could be, as I told you before. Note that in this case, floor displacement and constraint, unlike the previous case where you have given only the top displacement and allow the other to take it freely, take values freely. Since the constraints apart from the stiffness distribution is another constraint which guide the displacement, are imposed on the displacement, the loads acting on the structure have to follow a consistent pattern with that of the loading. Okay. So the load, there must be a consistent pattern of loading. Right? This consistent pattern of loading is calculated, okay, and we apply that, and after applying that we find out the displacement. That displacements happen to follow with the same mode shape pattern which you have considered, and we can find out the bending moment, shear force, etc. Right? So let me repeat it again. Here I am pushing at the top, no doubt. Incremental pushing I am giving, but at the same time we make sure that the other floors, when they are displacing, but this displacement has a unique shape, and that shape is the first mode shape. In that pattern only I am pushing. How do you do that? Experimentally or in real practice, that we will see later. Right now we are doing a theoretical calculation. Theoretically the problem can be solved and all response quantities can be determined. Practical implementation of this type of pushover analysis requires controlled pushing of each floor of the frame by controlled displacements. Okay, let phi be the mode shape and phi is the normalized such that the top of the building has mode shape coefficient as unity. Okay, then if you are giving a top displacement at delta t at any instant, delta t increment, then phi 1 in delta t, phi 2 into delta t, phi 3 into this delta t, they are the displacements at different floor. Okay. and I am incrementing my new delta T only at certain value, say 1 centimeter or 2 centimeters in that increment. Now then I can write down K phi delta T is equal to P, right? This is the force. And here you can see delta T is specified to us. Okay, I am incrementing, say 2 centimeter or 2 millimeter. Say phi is known, K is known, so I can calculate P. And P will have a distribution as the distribution like this. So now you can solve this problem. P is known. You apply that kind of P. This is a virtual P, right? For this theoretical problem, virtual P. You apply those P, find out the displacement, find out bending moment, shear force, etc. Everything done. All right. Applying this load to the frame, all response quantities of interest are obtained. So that is so far as the theory. Theoretically, I can calculate this load P and reverse back. That means again calculate with that P the displacements at all points, forces and other kinds of things. But when you are actually doing an experiment, what do I do? What are we going to do? For experimental study, the frame is driven by 4 actuators. No, one single actuator at the top will not work. So 4 actuators such that the incremental displacement given to the actuators in the proportion of mode shape from a single controller. So from a single controller we control the movement of these actuators, right? Push them in certain fashion. Which way we give the displacement? In the first mode shape. Resulting forces on the frame are measured. You can measure the forces which are coming, right, from the reactions of those actuators. And they will eventually be equal to the one that you have calculated. The transducers attached to the frame measure the displacement. Strain gauges provide stresses at critical sections from which moments and shears are at the and shears at the sections are derived. Values are compared with the theory. So in the actual experiment, what we do, we have not one pushing, you are not pulling like that. If you want to do it in a mode shape pattern, then 4 actuators should work. And this will be a controlled push with a delta T increment. And experimentally you can obtain from the transducers and the strain gauges. The strains, displacement, from the strains you can calculate stresses, from the stresses you can get back into moment, shear force, etc. So everything. And once you have got these values, you can compare it with the theoretical one, which we have described before. Okay. Okay. Now, up to this, if you have understood, now we are going from linear to the non-linear range. For linear modal pushover as described above pertains to linear range. Okay. There is no hanky-panky in between. Just very straightforward. However, pushover analysis is generally performed till the collapse state is achieved. Okay. Now this collapse is now defined in terms of displacement. Okay. Because it is now displacement control. Okay. So, and you know what you mean by displacement control now. So that means we push up to a certain specified displacement, and that is what we are saying, and this is our collapse state. Therefore, the inelastic deformations do take place at various sections of the frame. Okay? So we are not, that means since there is a desired displacement, I do not know at what point it moves from elastic to inelastic, but it does. In order to take care of the inelastic effect, a nonlinear static analysis is performed as the frame enters into the nonlinear range. The solution is carried out is incremental analysis in which at each increment the stiffness matrix of the frame might change as the members pass from elastic to inelastic state. Okay. Now here again some little bit of inelastic analysis comes into picture, which okay. Now which I'll try to, this inelastic analysis is a little bit more elaborate than what I am going to explain over here, but I am explaining briefly to give you an idea how we do it. Okay. Say you are pushing in this particular way, so that after some push displacement, say there had been two plastic hinges which has formed. Okay. How these two plastic hinges has formed and how to trace that part is a inelastic analysis part. Okay. That is, not so easy to explain in this class, but subsequent things will give you some idea, subsequent explanations. Say at that stage, I am giving an incremental displacement of delta U. Okay? And after that, when you stop, after delta T increment, say there are two more plastic hinges have appeared. So, in place of two, there are four plastic hinges are there at the end of the displacement, say. Then what we will do? Firstly, who will detect that extra two plastic hinges? The computer will detect. The moment you give a push, computer immediately at that stage will show that two plastic hinges has appeared on these two beams with some color. I'll talk about this color later. Okay. But you know that now four plastic hinges have come. Then what has happened? From two plastic hinge to four plastic hinge it has come to. So during this increment, somewhere these plastic hinges, extra plastic hinges have started forming. Alright. And at the end, you have four plastic hinges. Okay. Now I am performing an analysis for that. So when I am starting the analysis, K matrix that I write, in that K matrix I take this frame, and whenever I have that plastic hinges, I assume that place there is only a hinge. That means it cannot take no more bending moment, no extra bending moment, right? So at this stage here, it has taken MP values at these two places, MP values. Okay. Now I am pushing little bit. During this push, these two ends cannot take any moment. It will stay at MP. Alright. That means this curve, elastoplastic curve. After MP, without increasing moment, the displacement rotation will take place. Okay. So that has taken place. So the MP remains same, and as a result of that, when I am forming the stiffness matrix for the next increment, I simply insert in place of plastic hinge an ordinary hinge. Ordinary hinge means it cannot take up any moment. And now you know how to find out the stiffness matrix. Okay? Let me give you a hint to you, which you have already done. Say I am trying to find out the stiffness of that joint, right hand side joint. Column will be 4EI by L. Down column will be 4EI by L. For the beam, what it will be? 3EI by L. Because on that side there is a ordinary hinge. Alright? That's how you modify your stiffness matrix. Okay? So, at that stage, when I am going, my stiffness matrix is modified. And that modified stiffness matrix takes care of the plastic hinges that have taken place. With that modified stiffness matrix, I multiply it by delta displacement. Delta displacement is known to you. On the top you have given it displacement, right? And multiplied the flow by the mode shape factors to find out the other flow displacements. Okay, and you carry out the analysis. And during this analysis, you are assuming that over this increment, the stiffness have remained unchanged. It has not changed. And you arrive at two more plastic hinges at the end. Okay? But during this push, it may so happen the plastic hinges have started forming at a little bit of push, right? Than the push that you are giving. Say maybe 1/4 of the push. During that time, one plastic hinge formed, right? Then maybe 3/4 of the push, the extra two plastic hinges are formed. So I do not know at that during this period. So I should basically not take the constant stiffness that I have generated over the entire increment, right? Because the hinges might have formed gradually over here, and obviously the stiffness might have changed. So how to take care of this? Right? So one of the there are two approaches. One is either you make your delta T very small, delta E very small increments. In that case, most probably, during the increment, the extra hinges will not form. Only at the end it will form. Right? This is one way. But in that case, your solution procedure or the time taken for the solution will be more. Other way is to modify it, and that is what is there in most of the softwares. What they do is that the moment they find that extra two plastic hinges are formed, they pull back to the previous one. Okay. And when the four hinges are formed, with that they compute another stiffness matrix. So one stiffness matrix with two hinges, other stiffness matrix with four hinges. Okay. And they pull back the system to the previous one. And they make a average stiffness. That means 0.5 K1 plus K2. Average stiffness they take. And this is quite rational. So somewhere in between, the hinges might have formed, and the actual stiffness is an average stiffness of 2 and 4. Okay? So with that you perform an analysis and see what has happened. If you find that, yes, again this 2 is there is no problem. Okay? If you find that no, then again whatever scenario you get at the end, with that you make an average stiffness and continue this procedure till a convergence is achieved. Is that clear? Yes or no?
Yes.
So the softwares basically have that. They incorporate this average stiffness. But if you wish to write your own program, you may not bother about it, provided you take very, very small increment. Okay. With this incremental displacement is provided again from the pullback state, and it is if the same state as the bata diya. The procedure is continued. At each increment, the stresses and other responses are calculated and added to those of the previous step. So once you have found out the incremental displacement, and so you can find out for the incremental displacement what is the stresses, incremental stresses, etc. You calculate, add to that. Now, the pushover analysis finally is important in getting a plot which is called a capacity, plotting a capacity curve or shear force versus displacement curve. All right. So that is what my interest. So what I do for each increment, whatever is the delta Vi, which will be a summation of delta Pi, that means all force, whatever is the incremental forces that you add up, I get delta Vi, which you add to the previous Vi, and go on like this. And finally, at each displacement, I get a value of Vi. Okay, and we have a plot. Okay, so then one thing, important thing remains to say. Now that is about the backbone curve in the pushover analysis. Okay, and that backbone curve is about specifying what happened. Pani.